Okay, in this video we're going to wrap up our proof of concept little system here by adding in a trigger box. And what I mean by trigger box is we're wanting to put one special box into our level in which the ball can strike, and when it does, it's going to act, well, like a trigger. Meaning that, one, it needs to go away, but it needs to activate all of the other boxes so that those boxes can die. Basically, they can begin receiving damage each time a ball collides with it. And after a ball collides enough to kill off all of the box's health, well, the box is going to die, which means it's going to disappear. But what we're going to do is when all of the boxes become damageable, we're going to set their colors to yellow, and as they receive damage, the colors are going to shift through the spectrum from yellow to orange to red, and then dead. Okay, so that's the plan of attack. We will be adding a new class this time around called Trigger Box. We did not want to add the class at the very beginning here because we've kept the primary focus of this entire project on just having a ball bouncing around off of all of our rectangular boxes on the screen. But now we'll go ahead and get this new class set up, and then we'll add the appropriate code inside a box so that, well, box knows about, is it destructible, does it have health, and stuff like that, and then we'll get the trigger box all set up.
All right, so first we'll take a look at box. And inside of box, we need to set up a couple more fields. We need to have an is destructible field, so we know whether or not the box can even receive damage. And then we need a health field, so we can record how much damage has been taken. So both of these will be public. The first will be a boolean, and it's called is destructible.
Okay.
And then the other field is going to be a public int called health. And we'll go ahead and just initialize that to 100 right here. Alright, now with these two, we need to go down in box and implement process collision for the box. And inside of process collision, what we'll do is we'll do a check and see if we are destructible, and if so, take damage upon collision.
And of course, adjust our color, and if we're dead, remove ourselves.
So the check is going to be first to see if we're destructible. So if this dot is destructible, then we can go through and do damage and possibly removing this box. The first thing is we'll record that damage. We'll say this dot health will be decremented by 25. Then we're going to take that new health value and figure out what color that should be. Basically, we want to have the box shift from yellow to red. We're going to have all the boxes turn to yellow whenever the trigger box is hit. So the interpolation here, we want to go from the color yellow to the color red based on how much health is remaining. So what we'll do is we'll use the linear interpolation function inside of Math Helper to take where we are in our health against 100 and use that to find a color.
Right.
And I'm going to store this color in a byte because I'll use this to make a new color here once we find it. We'll make byte G since it's actually only the green component that we're going to be affecting. And that will be the casted result of mathhelper.lerp for the values 0 to 255 over a floating amount. Now we need to find what percentage of the health we have left. We know if we have some point value out of 100. Now if we take the current value and divide that by 100, knowing that 100 is the max, that will give us some percentage in the range of 0 to 1.
Mm-hmm.
So we need to take the float casted of this dot health divided by 100. And that will end off the lerp.
Now we can turn around and use that byte inside a new color.
And let me make sure I use equals assignment when I make the byte. Alright, so now we want to take that and make a color for this box. So we'll take this dot color equal to a new color where we can feed in 255 for the red component, whatever we had found in G for the green component, and 0 for the blue component. And one last thing we need to do is to do a check now that we've decremented health, have we actually been destroyed? So we need to see is this dot health less than or equal to 0, because if it is, and that needs to be phrased in the form of an if statement, if this dot health is less than 0, then this box needs to be removed from the actors list. Actor.actors.remove this actor.
Okay.
And that takes care of process collision. So let me make sure that there's no errors introduced. Now we can focus on the trigger box itself, what's actually going to cause this. Though before I jump too far ahead, there's one small thing I want to do, and that is to go back to ball and make sure that this process collision gets called for any box that it's colliding with.
Okay.
So over into ball, here we have all the process or checkbox collision. At the very end, if we had in fact collided with the box, we'll make a call to that box's process collision method.
Good.
All right, now we need to focus on the trigger box. So the trigger box is of course going to be a completely new class. So go over to classes, add a new item, and that item will be a trigger box. And let's clean up the namespace a little bit, maybe add some using statements. Let's see, what were we using over in box? XNA framework and graphics, we'll grab those. We don't need collections or text, so we'll paste them over.
We'll go ahead and make sure we extend box.
Trigger box extends box. And now we can put together an implementation for trigger box. First of which is going to be the constructor. The constructor for the trigger box needs to do a few things. Starting out with the fact that boxes are they're destructible set to false by default. Right now that's because of the field initializer. We could set it up just manually if we wanted, so it's obvious.
Right.
But even if we leave it alone, is destructible is false by default. That means any spawned box is indestructible.
Right.
The trigger box is going to be the only destructible one, so we need to make sure we set its destructible field. We'll also set its color to red, so it's easily identifiable. And then one final thing we'll do is set its health to 1, so that it only takes 1 hit to kill it.
Right.
So the constructor will be public trigger box, and we need to take in width and height so we can pass that along to the base constructor. So we'll take in an int width, an int height, and then call the base constructor with that width and height. And let's see, bracket that in, pull that back a little, and just for personal preference I'll grab the call to the base constructor and drop that back on the same line. So 3 things we need are the color, the is destructible, and the health. So this dot color will be set to red. This dot is destructible will be set to true, and this dot health will be set to 1. Alright, now the other thing we need to do is we need to override process collision, because trigger box needs some special handling in case of a collision, since it actually has to go through all the other boxes and make them destructible. So we'll make an override to the process collision method for box. And we'll leave the call to base.process collision in because we want all of those things to take place. Because nowhere in trigger box are we decrementing health. So we need things like health to be calculated in the base implementation. Now inside of process collision here, since this is a trigger box, we need to look through all of the other actors and see which of those are boxes and make any of those boxes destructible. So we'll begin with a for loop that will go through all of the actors. So actor, and did not mean to jump down quite so fast, actor.actors.count. And for each actor, we'll make a box variable and see if we can cast actor over to it. So box variable called box is equal to actor.actors sub I as box. Then if that box is equal to null, we'll continue on to the next iteration. And if it was not null, we actually have a box. Now we can set up that box to be destroyed or be destroyable. First, of course, is the is a destructible set to true for that box. And also we'll turn that box, or all of the destructible boxes, to yellow. So box.color will be equal to a new color of 255, 255, 0.
Okay.
And we still have our call to base.process collision, so that should be everything we need for the trigger box.
Very
Again,
nice.
I'll build, make sure that we have no errors. And now let's go back to our main scene and add a trigger box to the bottom of the map. Go over to game, and below, let's see, create demo actors. Here we have the series of boxes. Right below that, let's add in a trigger box. So make a trigger box called, a variable just called tbox. And we'll set that to be equal to a new trigger box with a width and height of 32. And then we'll position that box at the bottom center of the screen. So tbox.position will be equal to a new vector2 at center of the screen, so screen width divided by 2 for x. And for y, we'll have the screen height minus the box's origin, so we have it resting on the very bottom of the screen. So minus tbox.origin.y. And that should place a trigger box on the very bottom of the screen.
Very cool.
So let's build and run. Now looking at this, it might take a little while for the ball to actually reach. So one last thing we could do would be to add some code that would spawn a series of these bouncing balls that would
so close.
that would reach the trigger box more quickly. But there we go. So eventually it has reached. All of the boxes have turned yellow. And you can see as the ball starts to hit them, they turn orange, then
and
red.
One has been damaged and destroyed, not including the trigger box, of course. 2 have been destroyed. But yeah, it would definitely look cool if we added more of these little spheres in there.
And just to make it interesting, let's actually spawn a circle of spheres in the center of the map and have them all go out in an outwards direction until, of course, they start colliding with things.
Sure.
But this will add a more interesting effect and will also allow us to test how quickly the scene gets destroyed and give more examples of the collision and damage handling. So what we'll do for that is inside of create demo actors, let's replace the ball spawning with another specialized loop. Now for this one's a little bit more complicated, so I'm going to make some more variables to describe the various elements of this circle of spheres that are being spawned. First of which is going to be an integer for a count, how many of these spheres to spawn. So let's set count equal to 10. Next will be the speed that all of these travel at. So I'll make a float called speed, which I'll set to 3. And next we'll have a circle radius, meaning that when we spawn all of these in a circular pattern, what's the actual radius of that circle? How big is it? So we'll make a float called circle radius, and we'll set that to 62. Now with these, let's begin a for loop to go through all the elements and count. So we'll do for loop for count. Now inside of the for loop, here we can put the actual spawning of the ball. So I could, if I wanted to, just copy this code, though I'm probably going to move the velocity line and just redefine that later.
Sure.
So we'll spawn the ball with using the variable name ball. But now we need to define some further variables to figure out exactly how we're going to describe and position these into a circular pattern. So let's move down to the first of these will be a float for percent around circle. So as we basically, since we're going through a loop of 0 to 10 in this case, a circle is going to be described by 2 pi. So we need to convert a range of 0 to 10 to a range of 0 to 2 pi. And I'll store this value in percent in a variable called percent around circle. So we'll do PCT around circle. And that will be equal to I casted to float divided by count. And okay, count lowercase, very good. So this will find in a floating percent, so at a range, this is converted 0 to 10 to a range of 0 to 1. And we'll use that later with pi to find where we should be. Now I'll also store the value of pi times 2 in a variable called full circle. I'm trying to go a little bit simplistic with some of these variables just to make it a little bit more clear so we don't have a line that has pi times a whole bunch of numbers divided by a whole bunch of numbers.
Sure.
So this next variable is going to be called full circle, and it will be set to the value of mathhelper.pi times 2.
Which gives you a full circle.
All right, one last thing, and we'll call this rotation offset. As a matter of fact, I'll get back to rotation offset here in just a second. I'll leave it out. The reason that we need this will be more clear when we actually see the ring of spheres being spawned.
Okay.
So let's just use percent around circle and full circle to figure out where we should be and set the exact rotation for each individual sphere. So I'll make a float, and rather than calling it rotation, let me actually call this angle. This would make more sense, especially compared to some of the A10 stuff we were doing earlier.
Sure.
So we'll set this angle equal to the value of full circle times our percentage around the circle for the current iteration of the loop, and that way we'll find an angle. So this way it converts it from a range of 0 to 1 to a range of 0 to 2 pi.
Mm-hmm.
And of course, all of this could be done more directly, but it makes it make a little bit more sense. So we're finding an angle, which is where we are on the current circle.
Sure.
So now when we have this information, let's set the velocity so that it's facing away, or so that it's facing down this angle. So we'll take ball.velocity, and set that equal to a new vector 2. And we'll use sine and cosine to convert this angle of radians over to a unit vector.
Okay.
So we'll use, we'll cast a float, math.sine for the given angle, and that should take care of x. So we could probably drop down a line so this doesn't go off screen. And then we'll cast a float, math.cosine for the given angle. And then that should finish off the definition of the vector, but let's remember to multiply that by speed, since that will in fact give us a unit vector, and we may want more than that. But being a unit vector is very convenient, since we can get a desired speed by multiplying it by whatever float value we want. Now that takes care of the velocity, but all of these would be spawning around the center point, wherever they happen to spawn. As a matter of fact, if the code builds, I might be able to show this. If we run now, of course we haven't set the position, so all the spheres will start in the top left corner of the screen, and some of them will immediately bounce off. But if we run, well, it's hard to see with the blocks in the way, but let me set the speed to really low. So you can see, watching the spread, you can start to see a little bit of an angle away from the corner.
Mm-hmm.
So we are in fact spawning around the corner, it's just a very small area. Let me find, where would be a good place to actually use as the starting point. Let me set, let's set up the ball's position to be a little bit different. Let's have, just after we spawn each ball, let's set its position equal to just about the center of the screen, but adjust it a little bit so that they're not right next to one of the blocks. So set the position equal to a new vector 2 of centered in x, so screen width divided by 2, and screen height divided by 2, but then offset minus 20. Let's see, where's that spawning? Right, okay, that's spawning, there we go. And now you can see what's happening where they all spawned directly over each other. They're moving out in a circular pattern, which is very nice, but they spawned all on top of each other. What we would like is to have a larger circle as a nice radius around, so we don't spawn between those blocks. So what we can do is use the same calculation that we'd use for velocity and use that to add on to position. It's almost like setting an initial movement and then going on. So we could take ball.position and increment that by a vector similar to this angle. So as a matter of fact, how much of that can I steal? I might do it like this just to save time. Let's copy the line where we set the velocity, paste that and change velocity to position, except we're incrementing instead of setting it. And then we'll increment it by the direction that the specific sphere should be traveling times the circle radius. So now, if we run, we see we have a nice large circle of spheres being spawned all around that one point.
Very nice.
And let me speed them up a little bit, and I'll show the current problem we have now. And if we speed these back up to the full value of 3, we have some of the spheres that bounce directly up and down, some of them that bounce directly left and right.
In this case, no left and right. If we just add some more spheres, though, we can get into a...
Maybe if we add one more so that it's an odd number.
So, go...
Well, let me try 8. I think 8 works well for that.
Yeah, there we go.
So now we have 2 that bounce left and right, 2 that bounce up and down. And the whole simulation looks nicer if everything is off just a little bit, so it continuously finds a new path throughout all the blocks. So what I'd like to do now is, let's take that entire circle. Let me actually set these back to very slow so I can show what this is. So let's take this entire circle pattern of spheres and take the entire thing as though we had rotated it a little bit.
Okay.
So to do that, let me define a final variable, a float rotation offset. Now let's set that equal to the value of a full circle divided by the number of spheres that we have divided by 1.7. The idea here is that rotation offset, if we took a full circle, we would rotate the entire thing 360 degrees and see no result. But if we divide that by count, we only rotate it by however much the spacing represents for each angle. Like, we would rotate it just enough so that if we had one sphere at the very top, he would now be in the position of the rightmost sphere, and the other sphere would have taken his place, so it would still look like nothing had taken place.
Mm-hmm.
But if we divide that by 0.7, we'll take the spacing between each of the spheres divided by 0.7, so we get a nice fine offset. And now when we calculate the angle, let's remember to multiply that angle, or actually
add it in,
just rather offset it by the rotation offset. And now you can see that the sphere on the right is a little bit going up and to the right, and then the other one's up and to the left. None of them are traveling on an exactly straight path.
Sure. Go ahead and set it back to 10 now real quick.
The number?
Number of, yeah. And then even the one going straight up and down. So everybody here. Now you can go ahead and set speed back to normal, and we can watch how this plays out.
So we have a nice set of bouncing, and then we hit the trigger box, trigger all of the boxes to be damageable, and now there's lots of spheres bouncing around the screen to quickly take out all of the boxes.
Yeah, very nice.
But note that even when a box dies, that the sphere still bounces off of it. So that one, the top one just died, and which is going to be the next one to die, and then top one again.
Close this down. Now go ahead and add in 50 of these guys.
50 of the bouncing.
Yeah, even though of course we did not set out to design this to be efficient in such a way that we could handle, thousands of bouncing spheres. Of course we could do that, but that wasn't the goal of this particular proof of concept. It was just doing collisions with our boxes and making sure all of our bounces looked really good, because we need to come up with a game, Battle Blocks, that has only 2 spheres bouncing around the screen. So it needed to be able to handle only 2. But let's see how 50 look. Oh, yeah.
That's like a lot. And it also clears the field very fast.
Yeah, that looks really good, especially if you just pick one and focus on them. All right, excellent. Okay, so the assignment now is to produce battle blocks the way we discussed it in the very first video when we first introduced you to the game. So with that, hopefully this proof of concept and how you can go about doing collisions and working with the velocities, making the bounces look really nice. Hopefully all that will become very valuable to you, and you can put it to good use in your game. And once again, please feel free to post those games over in the XNA classroom. And with that, that will wrap up this video. Thanks a lot.